Hi, I'm Philip, and in this video I want to show you my new methodology for accuracy testing 3D scanners. So what I previously did with all my scanners, you may already seen it, I used basically a calibrated micrometer to then place it on a turntable with markers placed on it. I also used some 3D printed marker geometries, and then I scanned this whole setup with the scanner 6 times per scanner or per scan mode to then measure the distance between the spindle and the anvil faces. So this distance basically. The nominal was roughly 125 millimeters. So this is like a 125 millimeter micrometer, and also I have this 125 millimeter standard. But there were quite a few opinions about this measurement approach or this methodology approach, and basically all of them are right. So this isn't by far the best option. So only using the pin would have been better, to be honest, because this is the standard and this is like only calibrated with the standard. But I started with the micrometer and I wanted to keep the methodology as similar as possible for all my testing, simply to have like a uniform testing approach. So the scanners are at least relative to each other, better comparable, but not like to the absolute reference. So I hesitated a bit of changing the whole testing approach until I found a better solution. And I finally found one, or I finally got one. As you may know, there are ball bars. So these are like basically like the one here, or the one you can see here. This is a small one. You have 2 spheres and they are connected in some way. On this one we have a carbon base plate in like a soft cushion wooden box, so it is protected. And then they are measured very accurately in a certification laboratory. And this can then be used for as artifact for testing accuracy. There are also bigger ball bars of like 600 millimeter, even over a meter, but the price is like increasing exponentially. So this ball plate, so it's a plate, it's made by Revopoint, and it's released I think a few months ago with the CMM series. So the first scanner to support this one but natively in the Revopoint software. So that's not the software I use for this testing approach, but with the latest Revometro Metro Y Ultra and the new upcoming Tracking SR. Basically, you can directly measure this ball plate in the Revopoint software and get like a live feedback on the accuracy of the scanner. So you type in the stated distance of the spheres, or you scan the QR code that contains the status distance of the spheres, and then you measure it, and you get a error. Initially, when I got the ball plate, I only had this reading. So this states that the sphere distance is 96.8680 millimeters, but not any uncertainty. I also released I think it was a Reddit post that I finally got a proper ball plate for testing, and there was again some criticism about without uncertainty it's worth nothing basically. Sadly, the information wasn't on the web store, but I was in contact with the support and I found out all the relevant parameters. So first thing, this ball plate is measured by a CNAS certified or CNAS accredited calibration certificate, or a CMM used to measure it has a CNAS accredited calibration certificate. So CNAS is the Chinese equivalent to the VDE or ISO standards. This is very good. Then the next thing is the expanded uncertainty of the sphere distance. For this one, it's 3.36 micrometers for KF2. So that's roughly 0.003 millimeters. When we speak about normal laser 3D scanners, any 3D scanners, the accuracy range is roughly in the rough distance of 0.02 to 0.04 millimeters single frame accuracy. So this is like an order of magnitude larger than the expanded uncertainty of this ball plate. So it's a good artifact to use. So this is the first, and then there are a few more specs about the CMM used on the source of uncertainty, but I think I will put a screenshot in the video. So this is the first thing. But now we can either directly measure it. So if I now start a scanner, so this is a Sermon P1, it's very convenient because it allows screen recording for while scanning or while using. So I can now just start a scan. My goal will be again to use 0.2 millimeters of point resolution with all scanners I test on this one. So you can see here 0.2 millimeters, and I can directly start with the scanning process. And as you can see, I'm quite quickly capturing the spheres. The good thing also for comparability of the scanners I use with this one or with the ball plate is that the marker location is predefined on the ball plate or on the ball, on the carbon base plate of this one. So this is again one less factor of one factor fewer to create a proper comparability. So now I scan the ball plate, and then I can export it. First fuse it, measure it, and export it to Quick Surface to measure the sphere distance. So I also have like a Revomeasure, but I guess I will use Quick Surface. I'm just a bit more accustomed to it. Or maybe I will fumble around a bit with Revomeasure. So I think I have a 3 years license that came with my Kickstarter pre-order of the Trackit. So the only limitation with the direct scan is that the sphere distance is quite small. So it's 100 millimeters. So this is nearly like the single frame area of most of the scanners I test. And so you can see we only have this very short tracking distance. But I wanted to have a bigger tracking distance to get a bit more of an impression of the tracking performance and potential drifting. To achieve this, I created this lump of stuff, or this monstrosity. So basically, I can now set it up and build it, and then you hopefully will quite quickly see what it is. So let's first start by assembling the arc or the sphere. Sorry, the circle, the tracking circle. So you can see here. So this, it goes like this. Then we have the first setup, and the next. Let's first talk about the circle. So what we have here, it's a 3D printed circle with so the center of this marker track. So here the center, it has 0.5 meter of diameter. So the circumference is roughly 1.5 meters or even a bit more. But so for the relevant sections, so the sphere distances, that's roughly 1.5 meters of tracking distance between them. And I could now directly scan it like this. So let's start it. And I will now again use the same mode, the same scanning mode here on the P1, and I can just start. And as you can see, it's happily capturing all the markers around the circle. But my main problem now is that I'm having an overlap in the marker detection. So here, currently, I only want to scan like the left side, but I'm also capturing markers here on the right side. And therefore, I didn't actually use the whole circle for tracking, but it just used for full or combining the circle here when I meet again. It just used the tracking information of the other markers too. So this will be the easy mode, and in the end, it's quite similar to the first testing approach. To remedy this, I just designed this small 3D printed plug-on part. And what I can do now with this, I can just insert a 3D printer print plate. So I just searched for quite sheet metal I had lying around, or any sheet I had lying around, and I have quite a collection of printing plates now. And what this allows me to do is, if I can start a new scan now, that I can completely independently scan the two spheres or track these two spheres from both sides. You can see now it is only capturing the markers on the first side. I can follow the circle with like a very slow and steady movement. And then when I arrive at the second side, you can see it's again only capturing the markers on the left side of the printing plate. So this allows me to simulate over 1.5 meters of tracking distance. And in the unfused state, we can even see, like here on the screen, that we already have a bit of drifting. Most of it will be removed with like the fusion process and the post-processing. So this is only like the raw data preview. But this shows quite nicely the possibilities of this. So if we go back to the other scan where I didn't use the plate, there we can see that it doesn't have any drifting because it could combine the two markers from both sides again. So my testing methodology will look like this. I will first do, or I will do two or three approaches side by side. So the first one is 6 times direct accuracy measuring only with the ball plates. Then the next one is 6 times accuracy measuring with this like construction around the part. And then the third thing will be similar setup, but with global marker capturing. If it's possible, of course, with the scanner. One additional remark, before you say, the whole 3D prints may be a bit flimsy and it's not firmly attached. I know, but while scanning, I'm not moving it, I'm not touching it. So this isn't much of a problem. So it would only be a problem if I start to like move it, rotate it, fumble around in the print plate, but this is not my goal. So additionally, for the global marker capture, I will capture a new global marker before each iteration of the scan process. So now, as we have talked about the scan process, I will show you one example of how to measure the sphere distance. So it is like repeatable or understandable for you how the measurement process will be looking. The scan is processed in Quality Scan, and now I already imported the mesh into Quick Surface to show you how I will be doing the measurement. So in Quick Surface there is the Extract Primitive tool, and the most prominent tool I quite like to use is this magic, I would call it magic brush. And for the brush you can set like the sensitivity value. So let's set it very low now, maybe to 0.88 degrees. You can see it doesn't select too much. But now I will increase it to 4 degrees. So this is the center value, and this is also the value I will be using for all the testing. You can see now the whole sphere is selected, and I can fit like mathematically defined sphere through it. I will do the same one for the second sphere. And now what I can do is I can jump to the analysis section and use the measure tool. And I will use the 3D distance. So this is like the direct distance between the 2 points. And it now snaps to the center point of the sphere. And I get the measurement value. And now let's add this measurement to the Excel sheet I will be using for the accuracy values. Like this. And here you can see on the left side, let's first look at the sheet a bit more. Here at the top, we have the nominal value. So this is the nominal distance of the spheres stated by Revopoint with the uncertainty of the measurement. And then here I have like the quality 7 P1 with 3 rows. First row is for the first test, so the 100mm tracking. Second one is for the 1500mm tracking, and the third one is for the 1500mm tracking with global markers enabled. So these two use the tracking or the marker tracking circle use. And per test we can input six values or measurement values, and then we get an average, a delta error. So delta error is relevant for the accuracy, a standard deviation of the measurement. So this is relevant for the precision or repeatability, and we also get extended uncertainty. This is a bit like mashup of the ball plate extended uncertainty and the scanner precision. But this should be like enjoyed with a bit of care. What you also will see is a comparison of the delta, comparing like the 100 millimeter tracking test to the 1500 millimeter tracking test. So these two values here are like delta of this, and the next one is delta of this and this. So now let's input the values, or the first measurement value. So it's 96.8395. And currently it will not be doing much, but what I can do, I can just replicate it for now to show you how it works. And you can see average, delta, and standard deviation of 0, because obviously the tracker is, well, the values are all replicated. So this is like the measurement approach I will be using. Another heads up, I won't be comparing values or results of the old measurement process to the new one, or accuracy testing process, because the methodology simply isn't good enough to compare across methodologies, but within one methodology it's okay, for my opinion. So I will now release this video to show you the process, and then I will start remeasuring all the scanners I have, or still have. Sadly, it won't be all from the old testing process. Or heads up, I sold my some S1. This one I can't be testing anymore. But for all the other ones, I can redo the test, and then I will just gradually release the results when I finish processing them. So have a nice day, and be back when I release the results.